Let's continue the lecture on numerical differentiation by discussing the finite difference approximation of the derivative in a little bit more detail. So let's first go back to the definition of what a derivative now actually is. And we want to talk about the derivative of a function f of x at a certain point x is a. Now, what is this? Well, the derivative of f at this point a is the slope of the tangent line to the curve of f of x at point x is equal to a. So the slope of this purple line is the derivative of f at a. And we denote this derivative using either one of two equivalent notations, so df dx for x is equal to a, or f prime, which is the derivative of f, evaluated at a. And mathematically, this concept of this purple line having a slope equal to the tangent of the line at x is a, mathematically this can be recast into this following limit definition, so that we have here a difference in function values between x is equal to a and x is equal to a plus a small increment h, divided by the difference in these input values, so that is h. And we take then the limit of h going to 0 to get the exact tangent line at x is a. Now, where does this come from? Well, let's say that we have an h which is not approaching 0, but it's in this case, a quite large non-zero value. Well, then this red line over here will have a slope f of a plus h minus f of a, so that's the difference in function values between this point and this point, divided by the difference in input values, which is h. And then we get that this is the slope of this line here. And we see that indeed if we make h smaller and smaller, so here we choose h to be about half the initial size of h, so we get then this line, so the slope of this line is now equal to this ratio. And as we take h smaller and smaller and smaller, we approach the true tangent at x is a more closely. Now, numerically, we cannot really deal with this this limits process of taking h arbitrarily small, but instead we choose a small but finite h. So we take h quite small, such that this line approximates the purple line closer, but we still have to take it as a finite value, because otherwise we end up with dividing 0 by 0. And that's obviously not defined. So in practice, what we actually do is, well, based on the way in which f is presented to us. So if we have a way of evaluating f numerically, well, then we will just evaluate f at an x which is sufficiently close to a. So we just take a small h, evaluate f there, and we evaluate this expression. Or if we are presented with f as in a table form, then we just take a tabulated data point for x is close to a. And this will lead to a set of different kinds of finite difference approximations for the derivative of f at the point x sub I. And so now note here that I have actually discretized the x-axis here. So I chose a certain increment h, and we want to evaluate the derivative of f at x is equal to xi. So we want to numerically evaluate the slope of this tangent line using function values at one of these points here. So if it were tabulated, then we would just be given these points, or if we can evaluate f, then we say that we limit ourselves to evaluating f at the points xi or xi plus 1, etc. Now there are, in this case, we will discuss 3 different strategies with how we can approach this limit definition of the derivative. And the first one is a forward difference scheme. So what we do is, well, in order to evaluate the tangent at xi, we will use function values at xi and xi plus 1. So that is 1 forward in x. And in this way, well, we can use this finite difference scheme. So we take the difference in function values of xi and then 1 point forward in x and divide it by the difference in x. And then this will be our approximation for the derivative or for the slope of the tangent line at x is equal to xi. So that's a forward difference, and we can do something similar for a backward difference. So just to note here, so this forward difference, it corresponds to the slope will be equal to the slope of this red line over here. Now moving on to a backward difference, well, what do we then do? Well, we use point I, and we use 1 point to the left or on the backwards direction of the positive x-axis. So we use a point I and I minus 1. And in doing so, well, we will evaluate f at these 2 points in order to evaluate the to approximate this limit function. So we just take the difference in function values at x is equal to xi, x is xi minus 1, and divide this by the difference in x. And again, we can see that this on the right here, this will be the slope of the red line as shown on this picture in the middle. And we will use that as an approximation for the purple line. And then finally, I'll also want to talk about a central finite difference. And in central finite differences, well, in order to approximate the derivative at x is equal to xi, well, we use point I minus 1 and I plus 1. So x is now in the center of the points that we will use to approximate the derivative. And we can do a similar thing. Well, we subtract the function values evaluated at these points by the difference in inputs or x values that we use to compute these functions. And this corresponds to this red line over here, which then serves, so the slope of this line serves as an approximation for the slope of the purple line. Let's now apply these finite difference schemes that I discussed in the last slide to a practical example. And in this practical example, what we want to do is, well, we want to compute for the function f of x is equal to x cubed, x to the power 3. We want to evaluate the derivative of f at x is equal to 3. So this means we want to find the slope of the tangent line to the function f of x at x is equal to 3. So that is at this point over here. Now, why do I chose such a simple example? Because for such a nice polynomial function, we can analytically evaluate this derivative. So analytically, well, we just apply the power rule. The derivative of f is equal to 3 times x squared. Yes. And then we can simply evaluate this derivative at x is equal to 3. So this comes down to 3 times 3 squared is 3 times 9 is 27. So that is the exact slope of the tangent line at x is equal to 3. That is the exact derivative value at x is equal to 3. Now let's try to approach this from a numerical perspective. So without using this analytical knowledge of the power rule, let's try to approximate this derivative. So numerically, well, we need to choose a spacing h, which we will use in order to evaluate the function. And in this case, let's start with h is equal to 1. And again, if you can evaluate your function, then h is a choice you can make by yourself. If you are presented with f in a tabulated form, then probably, well, virtually always h is decided for you because you cannot just simply pick any value x where you can evaluate f. But here we assume that we can easily evaluate f, so we can choose h is equal to 1. So xi, where we want to have the derivative, is equal to 3. And in that case, x sub I plus 1 is equal to 4. X sub I minus 1 is 3 minus h is 2. So looking at the graph over here, we can really note down these values of xi minus 1, and xi plus 1, which we'll use in our finite difference schemes. So let's start with a forward difference. And as seen in the previous slide, a forward difference is defined as such. So we take a difference in function values in the forward direction. So we take the function value at xi, we also take the function value at xi plus 1. We take the difference in function values, so that's the, let's say, the rise of this line, and divided by the difference in x value, so that's the rise over run, which gives us the slope of the line connecting this point and this point, as a approximation for the actual true tangent at point x is equal to 3. And we can then compute this. Well, so we had f evaluated at 4 is 4 to the power 3 is 64, minus f evaluated at 3 is 3 to the power 3 is 27, and we just divide this by 4 minus 3 is equal to 1. So we get 64 minus 27 as if we fill in this formula, which is 37. So this is our forward finite difference approximation of the derivative. However, we see that, well, we are quite far off from the analytical and the true solution. So this means that, well, we can take a look at the relative error. So the error is 37 minus 27, which is 10. And let's normalize this by the true value. So we are off by 37%. So this is obviously a huge error to make. We're making really quite a big mistake with this forward finite difference for this choice of h. Let's take a look if we can do better by looking at these other finite difference schemes. So in looking into a backward difference, what do we do here? Well, backward differences, so we use the point under consideration, xi is equal to 3. And we go backward in x to xi minus 1, which is 2. And we use those to evaluate this finite difference formula. So we get, again, f3 minus f2. So that's 27 minus 2 to the power 3. So that's 27 minus 8 is 19. And again, we're far off. Obviously, we can reduce this if we were to choose h smaller, but for h is equal to 1, well, here we have a relative error of about 30%. So this backward difference is certainly not much more accurate, if at all, than the forward difference. And this is also what we would expect if you have some kind of symmetry in your problem. However, let's take a look at the central difference now. So for central differences, well, what we chose to do was, instead of looking in the forward or the backwards direction, well, we just take our point under consideration, xi is equal to 3, to be in the center of our difference scheme. So we use 1 point backward and 1 point forward in order to evaluate this finite difference central scheme here. So here we have then that f evaluated at 4 minus f evaluated at 2. So this will be 64 minus 8. And in the denominator, we have 4 minus 2. This leads us to 28. And we see that this is already quite a bit closer to the actually true value of 27. So here we have a relative error of 3.7. Now, I already mentioned, well, if you want to really approximate the limit definition of a derivative, well, we should take h sufficiently small. And an h of 1 is typically not nearly small enough in order to approximate this limit definition in an adequate manner. So what we can then do is to reduce h. So let's, instead of 1, use 0.25. And then we see that our points xi plus 1 and xi minus 1 are much closer to xi. And if we then evaluate these same forward, backward, and central schemes, well, we see that for all schemes, we get much closer to the analytical solution. And these relative errors are also reduced. So now we have errors of about 8% for forward and backwards, and of about 0.2% for a central difference scheme. Now, if we compare these finite difference schemes, so for these two resolutions that we computed in the previous slides, we can take a look at the error for a forward finite difference, for a backward finite difference, and for a central finite difference. And we see that for each, so keeping the resolution h constant, we see that every time the central difference has quite a significantly lower error than forward and backward respectively. But also if we refine the resolution, we see that something interesting shows up. So what we did here is we refined the resolution by a factor 4. So we reduced h by a factor 4. We divide by 4. And then we see that the error in a forward difference scheme also roughly divides by 4. The error in a backward difference scheme, again, also roughly divides by a factor 4, so that is simply proportional to h. But when we investigate the central difference scheme, we see that this is reduced by a factor 16. So there is something going on. There is something that's causing this central scheme to actually be a much better approximation for the derivative than the forward and backward finite difference schemes. Now, in order to elucidate why this is the case, we will look into how finite difference schemes of arbitrary accuracy can be derived from Taylor series expansions in the next section.